Okay. Right. So we have 2 hours to go. So I think all of you have already recognized the lectures will be done fresh in the morning, 8 to 10. That's your Advanced Construction Systems lecture. The workshop will run as it is. And as we said, you will have 1 week online, 1 week on campus. Last week, it was on campus in Melbourne, Bandura. This week, week 2, students, the workshop will be running where? In Bandura, okay? And it will be accessed online in Melbourne. So students who should access the online lecture from Bandura, they got this channel. You can see this one, Advanced Construction System Online, right? So I think it's all set up in your calendars. Online workshop Bandura, you will have it 12 p.m. This week for you. Okay. Right. Any questions? Any questions about the delivery arrangement? So this channel, you can see, just to clarify, in case I have typically new students coming in week 2, contact me if you're confused. But for you guys, for this subject, you have 3 kind of, or each student is having 2 team for Advanced Construction System. This is the main one. That's how you access or where you find all the materials related to the lectures. This one here. And this one is for Bendigo students workshops when their turn is to be delivered online. When Bandura or Melbourne students turn to access online, they can use this team section. So you just enter here and you're gonna find a link to get into the meeting. Okay, so that's it about the delivery. Let me now go back to what we're doing today. Today, we are mainly going to be, I will be introducing you to the first topic, which is again going to be supporting your work on Assessment 1, which I will introduce to you this week. Assessment 1, you should be starting on it this week with your group, which you teamed in last week. And the topics and the knowledge I will be delivering to you today, this morning, will help you to work on it. During the workshop, which is Wednesday, whether on campus or online, I will be talking about the questions. So after I introduce you to the first assignment, it is about answering 15 questions with your group members. And I will be going through those questions during the workshop. So it's really useful for you. I will not only answer it, I will not answer it for you, but I will give you enough support to go through that investigation and determine the answer. So that's one. That was one aim, is to talk about week 2 topic, which is industrial buildings, which is a steel structure building. What's the advanced constructions methods there? Given like the lecture notes for this topic, they are about 30 slides, which I will take you through. So I said before really I start on it, what I'm gonna do, I will complete where we stopped last week. So last week we had that general reinforced concrete buildings lecture. And I had an intro questions just to prepare you to the type of questions you will be working with over assessments 1 and 2, and also most likely in the final exam. So what I'm going to do in the next 20 to 30 minutes, I will be closing off workshop 1 questions, which I ask you to look at. I did not finish. And we're going to go through them. I will wait for you guys to participate. Usually with the workshops, I want students to think and answer to really have the correct understanding. All right. Is there any questions about what I said so far, or you need more clarity? So basically what I'm going to do now in 20 to 30 minutes, I will be going through the workshop questions that you're supposed to be finished already in week 1. Any questions, or I can continue from here? Okay. Now, to access these materials, workshop questions, go to your LMS page. This is the home page for the subject, which I trust all of you have seen and looked at. So week 1, last week, you can enter it from here, and I've briefed you all about this. The lectures I've gone through, which was quite lengthy. The document is here. The recording for lecture 1 is here. The workshop questions, they are in this document here. Okay, so the document I will go through now, it is sitting in week 1. Week 1, don't get confused. I know this is week 2, but I just want to go through the questions before I start week 2. All right, so week 1 questions, they are here. The drawings that you will need to look at to understand and answer the questions, they are located in these 2 icons. So architectural drawings, they are situated here, and the structural drawings, they are located here. Obviously, the updated recording, I've had last week, I've already uploaded because we had completed last week. We used the workshops to complete our lectures and start on the workshop questions. So the records are here. Today's record, obviously, it's going to be in week 2. Right? So let me close this and open again the questions. Right. So let's look together to question number 1. Remember, these questions are not related to your first assignment. That was just to let you start putting your hands on reading the drawings and understanding the type of questions you're going to be looking at. Question number 1, determine which note on sheet number 1 protects neighboring properties and underground services. So can students really look at the drawings? As I said to you, the drawings, obviously, just to give you a support there, such note, did I tell you whether it's in the structural drawings or architectural drawings? No, I did not, but SO1, it is the structural drawings. So let me open. Yeah, it's already open with me, but I will open it again. Let me give you 1-minute briefing. I did this quickly last week. This was the project that we're looking at for workshop 1 questions. It is about a library in Melbourne, and it is 2 floors. The first floor, it's the ground floor. However, the ground floor was lifted above the ground. Usually, if I go to these are the architectural drawings where we get a say and talk about dimensions and all kind of architectural features. Which again, construction engineers use to build because they need to implement and apply all what they want there. So what I really want to show you here is a section or elevation, which will help me let you know about, here we go. So this is the building. This is the ground floor. As I said, it's got a subfloor. So for, I think it was for flooding reasons. So for flooding, they needed to lift up the ground floor above the natural ground. And it is usually you would see the ground floor, it is just a slab poured on the dirt, on the soil, but this was not the case. So level 1, it is as shown here, and level 2 is suspended. What type of slab is this? Just from the quick look, what do you think the type of slab we're seeing here? That's what the architect is drawn. It's not structural drawings, remember, because usually, as I said, structural engineers work with the construction engineers and work with the architects to update the drawings continuously. So what type of slab we seeing here? Level 1.
Concrete.
Yeah, but it's got its own feature. Yeah, they're all correct. The material is concrete, but what system? It is the band beam slab system. So there are band, obviously there is a band beam here on this side. There is another band beam on the right side, and this is a slab. We called it last week. It's a band beam slab system, right? It's not a flat slab. It's not a flat plate. Flat slab and flat plate, they have no dropping for the beams. They are flat. Okay, so make sure, guys, you know what we're talking about, because these kind of questions you would need to know. So that was just a briefing about what the architect does. And then if I go back, let me see what else I'm going to show you from the, so sections, elevations, more sections that would help the builder to remember. The builder is not only building the structure and going away, they're going to build everything up to the door keys, right? So all those finishes, definitely it's something you would need to know about, because usually structure may take even less than half of the time of the construction time. The structural frame, to build it, it may take maybe 1 year, but the rest may take more than a year. Or to build this structure, it may take 6 months. And architecturally, to get it all finished, you may go all the way to 1 year. You need additional 1 year. So don't think that only structural elements you're building everything. In this subject, yeah, we're focusing on advanced structural systems that really construction engineers look after. So that was just for your information to know the extent of construction engineers' role. Yeah, so that was just what the architect want the builder to do. And definitely, usually architects, when they sketch these things, they work with the structure engineers who are going to be sizing up all the elements. You can see the stairs, throats, the slab thicknesses, the columns sizes and locations, and they end up putting them at wherever the engineer wanted. Okay, so let's go now to the structural drawings, which are open. I trust they are open. Let me see if it's this one here already. Is it this project, or that was something else? No, that was something else. Let me open the structural drawings for this project, and then you can answer a question, or maybe someone else already answered it, because I think we talked about this last week. So these are the structural drawings for the same project. Okay, I said to you last week, typically the first pages, in this case, it's only one first page. It talks about general information, which construction engineers need to read carefully, because they are limitations that the engineers are putting there, or the project is putting there, and they need to be careful about. All right. They talk about the quality of concrete you need to use, all the requirement you need to build your concrete elements, which you talked about. So they definitely need to be follow the standards and references construction engineers need to follow, which they would, yes, know about over the years, but you always need to be, maybe there are special things. Maybe in a new project, you got outdoor areas, and the engineer here in this project specified the new materials to look at. So that's where you would typically need to give it a run for 1 or 2 hours to understand what limitations. For example, under the steel structure sections, engineer somewhere here will tell you any steel column, you're going to place it outside in the environment, you have to galvanize it. You have to protect it from corrosion, right? So this is the construction engineer's liability now, because they have been given this instruction. All right, the engineer won't be saying this inside the in the tables, or the, you know, where they specify the steel beam. And there are many other things. Yeah, so all same thing here. We're talking about concrete structures. In case you have a steel column embedded inside concrete, you have to galvanize it. Now let's go back to our simple question. Question number 1 is telling you is sheet number SO1. This is sheet number SO1. I know someone will ask me, this is, maybe I just removed just to reduce confusion. and conflict of interests. I've removed the sheet numbers, but you have them here. The drawings you have, they're basically following this kind of sequence. Sheet S001. This is the plan or the drawings I'm talking about. I'm asking the students to go over to look at those notes and tell me which note numbers, or which notes, what are their numbers, which are asking the engineer to be careful, the construction engineer to be careful when they dig next to neighbors or underground services. Can someone answer me?
Footing note number 7.
Excellent. Let's have a look together. Footing note, so F number 7. Perfect. Yeah, that's the one. So you can see here, obviously, it's telling us simply, usually guys, if this is your building, building something new, you're going to have a footing, and sometimes we have some blinding under the footing. Then there is, based on the soil report, there is an angle of repose. Now, what does this represent? It represents how the building or the footing is pressuring the soil. It's the pressure always distributed by an angle, which goes between 30 degrees to 45 degrees up to the type of the soil. If it's sand, going to be 30. If it's clay, going to be 45. Now, what you need to measure is this distance. You need to make sure that your footing going to be away from the pipe, because number one, maybe this pipe will get damaged or leak, and council or like authorities want to come and fix it. So when they dig next to your footing, it will be safe for the building and for them, right? Number two, you don't want to put pressure on the pipe. So that's the protection we are required to be looking after, right? If there is a pipe for Melbourne Water or a pipe for Yarra Valley Water, you know, the Yarra Valley Water is one of the main authorities in supplying water to properties, or even placing the waste pipes. So can someone ask how they would know about the location of the pipes? Just for your information, the architect would typically document them. Yeah, it's one of, you know, when I said to you, when you get a project, you would need to survey and research about it. One of the things there is an organization which looks after this, dial before you dig. They will supply engineers or construction people with all the pipes located around whatever property we're talking about. And with the well-documented projects, usually the architect will be seeking for such information, and they will be placing it on the site plan on their drawings. Like if you go to the site plan, I'm not sure, like for example, it's the same project we're talking about. If we jump, maybe we didn't have a site plan here. Yeah, I can't see any services pipes located around here. Yeah, so still, if not, that's where the discussions need to happen, just to make sure your footing won't be sitting. And also, for given that you are the builder, also you need to check that they are documented on the structural drawings as well, right? Going back, that was there is also another, the one that F7, it is to do with underground services. What was neighboring properties? What about neighboring properties? Which note is actually reminding us about it? F8. Okay, F8, same story. When you're going to be building a footing, you need to make sure that footing won't end up pushing, or put it this way. If you're going to be excavating, right? If you're going to be excavating a trench next to existing building, you need to make sure you won't be disturbing the soil, which is actually supporting the building. Okay, so before this excavation here on the right, Let me just use my laser. So imagine this is not done yet. There is no excavation, and this was already there, right? Before you excavate, you need to make sure you also respect the angle of repose, all right? Otherwise, we have to do other arrangements, okay? So there is different things we're going to be experiencing during our projects. I think the project we're looking at, I mean, week one, does not have the story, but the ones that you're going to see later will have. But let me share with you something else. Imagine with me, this is here. I will just draw a footing. This is an existing footing, okay? This is an existing footing and the soil is here. This is the soil. And for your building need to be just next to the existing footing here. All right. And the depth of this existing footing was found to be, for example, 600 deep. Okay. Your engineer, for whatever reasons, because you're carrying maybe higher buildings. So I was saying that was the footing, and that means they have a wall here, maybe brick or block, it doesn't matter. That's the neighbors. Okay. Now, your footing needs to be, say, 1 meter deep, which is deeper. Okay, let me just draw it. Sorry, it's a bit because I'm using my mouse now. So this is your new footing, which needs to be how much deep? 1 meter. 1, 0, 0. Okay. Now, definitely, you're going to tell me based on this note, I cannot do that. Can someone tell me what else can be done? So the orange color, it's the new footing, because you need to build your new wall as well. So what else can be done? Now, why we cannot excavate? If you're going to excavate a trench hard against a neighbor's property, you're going to disturb their footing, and cracks may happen, and you're going to end up fixing it for them. So what else can be done? Any ideas? Any thoughts? We have options here, and we will be talking about over the semester, but a quick answer here. Yes, definitely, we have to stop at the neighbor's footing. We have to stop here. If it was not enough, then what we can do, we use board piers. Board piers, they're going to be every 2 meters. So if you look to the plan view, if like a plan view, say this is your plan view. This is the orange is our new building. This is, oh, sorry, I know. We're going to look at this slowly, but while we are on the topic, let me talk about it. This is our new side, and the red is the neighbors. Okay, so what I mean with board piers, it is we're going to be putting a board pier every 2 meters, because when you're going to build or excavate for a board pier, you won't really disturb or affect or impact the neighbor's footing, the red one here, because you're making a hole every 2 meters. So really, it's not a problem. You won't really stress out the soil. Okay, so these elements here I'm showing you, the one I'm hatching with red, they are circular board piers. They're going to be deepened to wherever the soil engineer wants, and you're going to be placing these guys wherever safe for the neighbor. So for example, you place them, and again, who says that to you? The structural and the geotech engineer. We place them apart from each other to not really stress out the existing footing. And then on top of them, we're going to be building a shallower strip footing with adequate reinforcement to act as a beam. And that's the solution here. Okay, these are just technique. We're gonna be in our assignments, especially number 2. We're gonna be talking about such situations. But I just want you from question number 1. I just want you to know the importance of understanding these conditions, because they may they may be a critical issue during your construction cycle. And yeah, if a damage happened for the neighbors, you end up fixing it to them, which is a cost and time issue. All right, any question about this? So yeah, in the final exam, you may have some type of questions about this. Yeah, you may be given some dimensions, right? And tell me, can you do the excavation or not? And how you can solve it. Why not? Because what I did, I discussed it with you, and it's something you have experienced with me. Let's go to question 2. Can you guys read it and start giving me answers? Now, in my assignment, in the assignment or your first assignment, when you have questions like this, you're going to be given how many of them you are required. Like here, it may look like it's an open question, but you're going to be given a limited number, which you're going to see when I brief you about assignment 1. So identify the structural elements required to construct the first floor of the property. Which sheets must be reviewed, studied by the construction engineer to identify the components involved in the building, in building the first floor? What is the vertical load path of the identified framing? So let's do it by one by one. Identify the structural element required to construct first floor. So which sheet you're going to look at? Can you give me the number? Which sheet you're going to look at? Structural drawings. Which sheet you're going to look at? Can we walk together? Which sheet you're going to look at to determine what components are actually carrying? Okay, 4, 6, 7. Let's look at number 4. So the way I'm counting them, I think you're looking to, if I'm going to look here, it's not used. But what I'm going to do, I'm going to say 1, 2, 3, 4. But 4 here. See, I'm seeing some answers at the chat. 4, 6, 7. All right, I would. All right, so I've got students telling me the same thing. 4, 6, 7. Yes, this is giving us some details and schedule. But hang on, I'm talking about question number 1. Let's look at question number 1. Okay, so look, yeah, that's what I just said. Students may look at this as an open question. Some people required to construct the first floor. Some people may start from the columns. So because they're gonna say the way I looked at it, you asking me how I can build the first floor. So what they did, they considered as well the columns. This schedule, it's a column schedule. It tells the engineer or the construction engineer what type of reinforcement and how many bars you need to put in the concrete column. All right, so you've got 2 concrete columns in that development, CC1 and CC2, and these are the details: reinforcement, the bar sizes, the ligatures, which are these guys here. These are the ligatures, yeah, and the concrete strength, 50 MPa. So I may accept this answer because you thought the question is asking you about what's carrying the slab as well. The question was typically or more into the slab itself. So some students may not really think about this, only this detail here. They will say, this detail is important because this detail is about building the slab, and it shows me how I have to make sure the column is connected to the slab. So yes, this detail, it is required for building the slab, right? Same thing here. It just tells the builder how we're connecting the slab into the columns. These ones, this detail and this detail and this one here, they're really talking about the columns. So if the question was about the slab, I won't really worry about sheet number 4. Right, this is wrong. Whoever said to me this plan, what's this? Did someone say to me, no, nobody said 5. Yeah, that's fine. I don't think anyone said 5. Which sheet number was this? This was sheet number 5. So it's not, because this is the ground floor. This is the ground floor. Okay, it's a bonding slab running over steel beams, which we will talk about over the semester. So let's jump this out. If someone says to me number 6, it's wrong. I don't know why they said number 6. Can someone talk to us and tell us? Maybe he's gonna say, or she's gonna say, it is about this, so that will be acceptable. This detail is related to number 6. Sorry, to the slab construction. It just tells you how we're connecting. But however, I will not agree, actually, because we don't have steel in the first floor. So I don't know actually why this was used. Can someone tell us why they selected number 6? And if you meant to have this is number 6, yeah, can you unmute to have a quicker discussion? Why number 6 was selected?
Yeah. Hello?
Yes. Yes, I can hear you. Yes.
Yeah, maybe because the question is about the structural element. It doesn't say just only the slab. All the structural elements.
The first floor of the property.
Yeah, the structural elements of the columns are not the structure. The columns and the beams are not from the structural elements for the first floor.
Yeah, but we just need to be careful for constructing the first floor. First floor means I will open the architectural drawings. First floor means that we are talking about, I will open it from the architectural drawings. I'm getting there. Yeah, this is the first floor. This one here. That's it. The details that some people were showing me, it's about this one, the ground floor. Is it clear now? This is the first floor slab. So the question was asking the students which drawings or what structure elements, what are the structure elements in the system that would form up this first floor? That's the question, as easy as this. So I would not need students to worry about columns. I don't want the students to worry about this ground floor. No, no, no. Right, back to the question. It is identify structural elements required to construct first floor of the property. First floor is here. If in the exam, I will bring the same story and tell you the subfloor or the ground floor, then that's where you can go. Okay, but things will be even much clearer. It will be clear for the students. This is going to be written here ground floor, and here will be written further to the students first floor, and this is the roof. Okay, so can people try again and tell me which drawings they need to use for question number 2? Just give it another go and tell me which sheets you need to use if we need to construct the first floor. First floor, as I've just clarified to you, this one here. Okay, I start getting answers. So let's look at the structural drawings again, and I've been told 9 to 12. So let's go to number 9. Structural drawings number. Okay, some people are telling me 9. What about this one, guys? So the answer is, I will start talking, giving you the answers. This is sheet number 7. This sheet, read it. First floor general arrangement. This sheet, yes. Remember, guys, this was for week 1. I know you don't know terminologies and slab, but you need to know this for the coming weeks, especially when we talk about composite slabs. in the second assignment. So when engineers typically frame up or provide documents for concrete slabs, they provide 3 sheets. Ideally, the first one tells the builder, talks about the thicknesses of the slab. When it's called or titled to be general arrangement, it means that this drawing will talk to you about the slab system type. And this one, obviously, it's a banded beam slab because we have on this side a band beam. And we have internal band beam here as well. And we got a band beam there and a band beam there to support the slab. So this element, which is 300 thick, it is the slab. And this arrow is telling you how the slab is running in the one-way direction, up and down the page, right? This is what we call a general. Yes, you will need to read this to understand how the slab, or what are the structural elements in the slab. Now, my question was, what are the structural elements? Number one, you have a band beam, and you have a slab. And that's it. These two, the elements that really form up this slab, got a band beams and a slab. That's it. That's that. If other people, they say to me there are columns, I would say this is kind of acceptable misunderstanding, because you think that I'm saying to you how it was built. But the columns, they are the element under, they are carrying the slab from below. Okay, so this is the first drawing. There are other drawings similar to this. Now, this table here talks about the sizes, whether because we do have some columns sitting on top of the slab. We do have, it's kind of got other steel work. So that's where the engineers will tell you about the sizes. Now, if we jump to another sheet, this sheet, as I said, they give you another 2 drawings similar to the floor plan. The first one gives you first floor bottom reinforcement. There is reinforcement located at the lower side of the slab, which are documented here for us. If you zoom in, it's telling you the bottom bars here, it's 7 and 20. So we got 7 bars with 20 diameters. We talked last week about steel and their sizes. See how it's documented? 7 and 20 means we got 7 bars, 1, 2, 3. So they are 7 placed across the beam. Now, someone will tell me why engineers don't show actually 7 bars. It's going to be very messy drawings. We don't do that. We just put one line, and then we say 7 of them. And each one is 20 millimeter diameter, okay? Same thing, we need another 7 here, another 7 here. That's at the lower side of the band beam. You can see here, there is 16s at 200. That's what this means. It's in N16 every 200. So every 200 mil, we put a 16 bar. Every 200 millimeters, which is 20 centimeters. Again, we don't show them every 200. It's just going to be messy drawing. We don't do that. You will be asked, guys, in assessment to do such drawings for problems we will discuss. So it's good to have an idea. Your problem is going to be simpler even than this. So there was another band beam here, same thing. The engineer had showed you how many bars you need to put there. Okay. So answering the simple question, I was telling you what drawings, if your boss going to give you a drawing and tell you start thinking about constructing the slab, which drawings you're going to look at? That was my questions. First of all, which elements we have there? It's really simple. It's a band beam and a slab. Which drawings you're going to look at? You're going to look at this sheet number 7, sheet number 8, sheet number 9. Why? It is the details. This is talk to you about the details. Let's say these are the top bars. These are the bottom bars. All right, this gives you all the information how the bars need to be actually sitting. How much the bar you cannot be placed, the bottom one cannot be placed and stop just here. No, there's a regulations. We have to stop it with the distance L. Where is L? It's given to you on another document, another table here. Okay. We need to lap the bar. We need to make sure the lab is into the band beam. To clarify to you again, this was the slab, the 300 thick slab, and this was the band beam. How thick was the band beam? Can someone just go to the drawing back? How thick was the beam? How deep was the beam? How deep is the beam? Can someone read it to me?
450 mm.
Correct, 450 millimeters. Yeah, here we go. This is again the general arrangement drawings will tell us the thickness of the concrete elements, 450 deep, and the slab was 300 deep, running down. Yeah, that's right. Manoj, it is 450 deep. Yeah, and same thing here. This band beam is 450 deep. Here it's going to be 350, obviously, because there is a step here. Okay, there is a step in the slab because that was outdoor area and this is indoor, so they have a step. Okay, so yes, these drawings needs time from the engineers to look at. They need to have 4 or 5 hours or maybe 1 day or so to read and start writing down what we have. We have a band beam along grid 1. We have another band beam along grid 2. The band beam is this much of width. Which is 2.4 meters, 2,400. So yes, you need to start understanding how the system works. The band beam is supported on those columns, which are below. Same thing here. That was the answer for my first question. In question number 2, the second one, which sheets you're going to use? Simply the answer is you just need to see which drawings are talking or helping you to construct level 1 slab. So it's sheet number 7, sheet number 8, because it talks to you about the reinforcement details. I was talking about the bottom, same story. This one talks to us about the top, the upper bars, right? That's what you're going to need to read and also make sure to implement on site. Okay, what else? Yes, this sheet talks about all the detailing. It's really important to understand and read. Let's see what else. Yes, this one as well. This one tells us what we have to do when we have a step in the slab. We have to use a special bars. We call them Z bars. Okay. All right. So we can read. I'm not, guys, asking you now to master all this information. I just giving you a simple question. Which sheets you gonna be reading? Okay, just so you start having that, form up these minds. And as I always talk with the students, this is the language construction engineers use. Drawings, drawings, drawings. That's what you use to do your work, because we don't design from imagination. We design from plans. This one, I don't think it's you know, it's not really related. I can't see. There is just telling you here how, I think one small thing, it just tells us, this drawing tells us how the stairs are connected to the slab. So it is important. So the builder, can someone tell me by looking to this detail what he or she needs to ensure, what they're gonna do when they actually, so just to help you with this part is actually located. I know you can't pick this now because it's the first time for you to look at. This is here. This section, you can actually read it. This section is just here. You see, read this section, section 11. Yeah, it's here. That's the stairs, concrete stairs going up to the 350 deep beam. We jump back to the detail, to the stair detail. Here it's section 11. So can someone tell me, as a construction engineer, what you need to make sure it's the contractor did on site quickly? So we can jump to another question. It's faster to unmute and talk. Please do so. You don't know? Okay, the engineer will need to make sure they're gonna allow for such key. There is a key. This is like they're gonna put a foam right? They need to make sure this won't be straight line down. There is a key here that will create that kind of locking between the future stairs, because obviously they're going to build, this is like a construction joint. We talked about construction joints last week as well. So you can't build the first floor slab with the stairs. Nobody will do this. Usually you build the slab and the stairs going to happen in a different day, a different package, right? There is, someone may ask me how the contractors go up and down. They have a special scaffolding stairs, you know, around the building. So first day you're going to be building this side of the first floor. When this side of the slab, you can't do it flat. You have to allow for a void. Okay, that's one thing. What else we need to allow for? So first thing, you're going to put kind of a polystyrene foam, small one, as big as what the engineer said here. They said 90 by 35 key point. That's easy done. What else you're going to allow for? These kind of questions, that's what you're going to say in the final exam, right? That's exactly what you're going to say.
Steel bars for the stairs should be put beforehand in the beam, which is anchoring.
Excellent. So there are anchorage or starter bars, whatever you call them. There are these bars. You see them? You have to make sure you remember these bars. It's going to be a problem if you, so before you actually pour this slab, before you pour it, right, you have to make sure they are simple things on site. They're going to be maybe only 15 bars. And people miss these things. If you miss them, it's going to cost you maybe day, 2 days, and you need to call another company, another contractors to come. You have to drill and epoxy. If you forgot this, you're going to have to drill and use chemicals to put a stronger bar. So there are small details. If misread, not done, this will cost you just a day or two, and you know each day it means money. So that's it. So from this sheet, if people select it and specified which detail is used, so be it. That's really this plans. They are talking about the roof, which is not our topic. It's actually our topic for next week, or actually week 2 this week. This is the roof structure. Okay, let's jump back to our question number. So what else? Okay, can someone quickly brief me? What is vertical pathway? What's the pathway? What I'm trying to ask you here. The loads, how they gonna go? Let's talk about dead loads from the roof. What's the pathway of the vertical loads? I'm not talking about the. I'm not talking about the wind load or the lateral load. Vertical loads. What's their pathway? Like, let's start from the roof. Okay, so put this down, guys. I'll say it to you. The roof sheeting will be sitting on the purlins. These terminologies are important for week 2 topic. So you see those elements here? I'm going to talk about this because it's part of what we're going to talk about today. These elements here, they are the purlins. Okay, they form up the roof. They carry the sheets. The roof here, it was a metal sheet. Okay. The sheets are supported on the purlins, which are P1 and P1. They are documented on the table here. Right, so the pathway is the roof loading, you can say, goes to the purlin. Then who supports the purlin? Okay, that's where it's good to look at this section number 32. Section number 32 should be in the next. Here we go. So have a look to here. You see the purlins? They are supported on what? These are the purlins. They are supported on what? See them here. Who's carrying the purlins? Difficult. So the load path, again, it's starting from the roof sheets, then going to the purlins, then going to the roof beams. Okay, then from the roof beams, they're gonna go to the columns, which are above, like all those C1's columns. They're gonna carry those loadings. Then after that, the loading will go down. I'm talking here about the load path. I'm gonna go down to the concrete slab. Yeah, here we go. This is the concrete slab. So all the roof loadings gonna come through C1 columns. Then the ground floor load, in addition to the roof load, gonna go through the band beams or the slab, whatever the case was. So you got some columns actually sitting on the slab, so the slab will worry about it, right? So those the dead weight and the live loads from the roof and the first floor gonna be supported via the band beams or from the slab to the band beams, and then goes where? To the concrete columns, CC1s, right? Then CC1s will take all the load towards where? Can someone answer this very last question? CC1s will take the load where?
Footing.
The footing, that's it. I remember some students were saying to me, it's gonna take the load to the ground floor. No, the ground floor is elevated. So you see the columns, they are actually going through the ground floor, which was a special elevated floor. And then it will, you can see there are details which helps you here. How the concrete columns, you can see these are the pad footings. So each column, the CC1s, they got their own decent pad footings, the large ones. Okay, so yeah, after the banded slab system, which gonna carry its own weight, the concrete slabs are supported on the band beams, and these two elements, they're gonna carry the above roof. They're gonna take the load through the columns. From the columns, they're gonna go to the main pad footings like pad footing 3, pad footing 2, and so on. And that's really the story. Same thing on this side. Okay. Some students, I remember in the past, they mentioned the, and this is the detail, how the column is actually connected to a pad footing, a concrete column I'm talking about. Okay. All those detailing are like this one here, it's a different, it's just to carry the subfloor, that ground floor system. Okay. Any question about question number 3? Actually, we finished just question number 2. Question number 3, identify the construction characteristics of the first floor, which I covered already. Discuss the type of slab and its elements, list 5 characters. Yeah, can we list, okay, characters? So we talked about, what was the type again of the first floor slab? Banded slab. Correct, James? Slab. Yes, it's a banded slab. When I say characters, it means as well the features. What's special about it? So I know
it's a one-way slab.
One-way slab, excellent. Tick. That's it. Yeah. One-way slab. These are the type of questions you need to get used to. One-way slab. What's another character? Maybe something are new for you, so I'm more than happy to talk to you about. It's a composite slab, because this means, I think, I've given you information, and that's what you're going to learn over the weeks. This indicates the way how the slab is spanning, and it's got bonding. So it's actually composite slab. That's another feature. Okay, that's another feature considered. It is a bonding slab, a composite slab supporting the system above. So the type was banded beam. As characters, it is a one-way slab, that's it. And it's a bonding slab, that's another point we can mention there. What else we can talk about? Another feature you see about this slab.
There's a steel decking underneath the slab.
Steel bracing.
Steel decking.
Okay, this slab you're talking about, it's different. That was the ground floor slab, but here we are asking you about the first floor. Okay, we're talking about the first floor. First floor, I'm not sure, I think you are talking about the one at the lower side, which is not what we're talking about here. This slab, this one here, it's a ground floor slab. It's again, it's a composite, etc., etc. But this is not our. You may have this question in a different assignment or exam or whatever. Question number 3 is not asking about this. Yeah, just guys try to be precise and understand what we talk, and ask me in the workshops, okay, to make sure you know. But is there a special feature we can determine here in the slab? How it is braced? How you think this slab is actually stabilized laterally? Like, you know, guys, I know the structural engineers will worry about this, but also you need to remember, as a construction engineer, you need to make sure what you're building is right. Asking a question, small question, can save you a lot. You don't, if you're not sure about something in a construction process, you don't need to ignore it and assume. Assuming can lead to a lot of major mistakes. Giving a call to the engineer or the other design team is really typically useful, because there's a lot of issues when people build things and don't recognize who's actually stabilizing it. So another character is this building or this floor is stabilized by a block wall system. What really stabilizes if we need to worry about lateral loads? Who stabilizes it? We can't only rely on sticks, columns going out from the ground. Maybe the engineer did, but you can tell here from the drawings, we have those walls, right? The hatched lines, like this line, this one at this end. You've got another element here. They are block like shear walls. All right, so you can say the slab is laterally resisted by a reinforced block wall. If you're going to come here and read about it, it will tell you. You know, it's concrete wall columns under. So you need to go and determine, and on other drawings, you need what about, but they are basically block wall reinforced. Okay, and if I jump quickly through the drawings, it will tell you the details behind the block wall. Let me go to the other side. I'm not sure if they put it on these drawings. Let me double check. No, I can't see. Here we go. Yeah, that's it here. That's it here. You can see there is a block wall, and the block wall is a load-bearing wall, and that's how it's connected to the slab. Okay, so the slab, its lateral stability, right, is based on the shear walls, which are reinforced block walls in this project. Okay. Another feature or characters with them related to the slab, I will just help you with it. It's got steps. You need to understand and recognize there are steps in the slab. You got some steps in the band beam. So the band beam here is not flat in the top. It's got a step. In this case, you need to read and understand this, these details, which I showed you before. See those details? This will tell you how you're gonna frame up for the steps. Okay. So as I said, there are the band beams. They got steps within the slab frame, and you need to then apply such reinforcement details to get your steps done. In case S was less than 80% of the thickness, you use this. If not, you have other arrangements. Okay, they just gonna be more complicated where you need to put more cogs in your bars in addition to the Z bars. So if the step was smaller, you just simply leave the bars flat like this and use Z bars. We call them Z bars, and that's it. But in situations where the step is actually deeper, greater than 80% of the slab thickness, yeah, then you have to cook the bars as required. So you see here we have to cook the bottom bars, because they are under tension. Okay, so in summary, this is a feature you can take as in the slab. I think one of the other features which would be acceptable to mention, it is about the slab got starter bars. The slab got starter bars at its connections with the stairs, which we talked about. So features, characteristics means there are some detailing construction engineers need to pay attention to, otherwise they may miss the construction concept and lead to major mistakes. Like, for example, if you didn't recognize these walls are actually stabilizing, you may end up not building the walls. And I can tell you this happened a lot. So people go and build the columns, right? The concrete columns. And they said, no, let me delay because maybe his friend, the block layers, the block contractors, they are busy. So they say, don't come now, come next month. But hang on, you have to build the block wall before, because you have to physically connect it together, right? So you can't just say, I'm going to build it after. You can't just physically connect it. You can't just physically connect the block wall after you build the slab, because you have to physically let the slab sit on it, because you need to use the block wall to stabilize it for lateral load. So see things like this detail here. Okay. So I think I've listed those 5 special features with the slab, and we've answered this question. Question number 4. I think that was answered. I did answer this already, because I took my loading all the way from the roof. Yeah. So we will talk about this slowly over this. I mean, I will start. We started already the 2nd hour. I will start talking about the lecture. Yeah, correct. It's sheet number 13. Yes, I think people are on top of it. Sheet number 13. That's right. That talks about 13N, not only 13 area, it's 13 and 14, and that's it. 13 and 14. 15, sheet number 15. This one is the block wall I was talking to you about just before, but sheet number 14 and 13 should be used to build the roof. The elements, they are purlins, they are the roof beams, and they are the columns, and they are the roof bracing, which I will talk to you a lot this week and next week. Roof bracing, yeah, these guys, they are the roof bracing, which will stabilize the roof for us and will take the load to the wall bracing, lateral loads, right? And the load path, as I said, the sheets will put weight on the purlins will put weight on the roof beams will put weight on the columns, and that's it. That's it for the roof, because the first floor slab will take care of the rest. Okay. So guys, experience this question, which I've gone through. I've already talked about it when I covered question number 2. And okay, question number 5 is things we're going to be doing this week. So we're going to be talking about this definitely this week, whether in the workshop or even next week, because with the steel portal frames, we will cover it in week 2 and week 3. This week, week 2 and week 3, we're going to be talking about portal frames. And that's what you're going to be doing in many cases. I think, yeah, we gave it as much time as we can. Is there any questions you want to ask me about workshop 1 questions? So my only suggestion is to go through them, put all the notes, and these are, again, the type of question you're going to experience in the final exam. There are things that we have been talking about. Number one, projects that you have been experiencing, you have your records, you should be taking notes, and that's all. You won't be asked things beyond what we talked about. Okay, things that you have been experiencing with me, you may be asked about. But yeah, we took more than expected, but let me give you a break for 7 minutes. So it's 9:13. 7 minutes break. Then I will start talking about our lecture notes. So I will close this. Assuming you have no questions about the workshop. And I will be starting about week 2, talking about week 2 topic. At 9:20. Okay, so 9:20. Let's start on our week 2 lecture. Week 2 lecture is about industrial buildings, and the type we're going to specifically talking about of industrial frames are the portal frames, something similar to the very last question you looked at in week 1 workshop, the questions we just gone through. So this lecture note, or today's lecture notes, this one, in addition to week 3, the one we're going to do next week, they should support your work in depth for assignment 1, right? Which I will brief you about Wednesday after tomorrow, and we'll also start taking you through the questions group by group. So we have 15 questions, but we won't be doing them in 1 week. We're going to do them in groups. So it's really important to work with me on these things, on the topic. So what we're going to be talking about or going through is the loads. Now, I've already talked about these things this morning and last week, but I just gonna bring them again to you. Up to the details required. So loads and members, right? That's one. Number 2, frame design, right? Your construction engineers need to know they are engineers. So they have been studying 4 years an engineering degree where they do know the design concepts and fundamentals. And as I just gave you example, if you don't understand the construction or the design concept, what was in the architect minds and what was in the engineering mind, there can be an overkilling mistake in the construction. The example I just gave you now was the block wall. The block walls I showed you in the library projects, they were there to resist lateral loads. If for whatever reasons they were ignored, they're not built, and they were assumed to be just a feature architectural wall separating 2 rooms from each other, then that would add another 2 weeks on your bill to fix missing such walls. So they should be, if you understand that concept, you understand the frame design, that the block walls were actually there as a structural guide to stabilize the building from lateral loads, then you will build it parallel with building the columns, or you just must build it before building the slab. Okay, it's too complicated to do it after. That's one thing. Roof walling and bracing, we're going to cover these things. Footing and deflections, we're going to cover these things. Yes, some of those terminology, someone will say, why I should worry about deflection? Should the engineer be estimating these things? Yes, the engineers, but you also need to pick, if the engineers made mistakes, you have to go to them and fix it. You cannot, again, you are going to be the first contact point from your clients, from the users. Okay, so maybe I talked to you about those stories. The way you connect the members together may have been misunderstood, and that caused making your beams loose. Remember last week we said there are rigid connections and pin connections. Maybe the engineer was talking about pin connection, and it was built as the engineer was talking about rigid connection, the expensive one, the fixed one, and you ended up pinning it. That will make your members loose. So that means you need to know what we mean about deflections. Okay, and some notes. The reading materials, they can be, again, we have provided all the required reading materials on our LMS, but there is always additional. As I said, if we will be using some of them, then you expect to be assessed about them during the assignments or the final exam. If there are materials that I gave you them for your background information, then you may just keep it for your background information. The materials, the one steel, which gave us information, I will show you those. These ones give us the details of the purlins. The purlins and girts, they are the framing members for the structures we're going to talk about today and next week, the industrial buildings. And one steel website they got Lyset company, which is this one. So these kind of links, they are related to each other. It's kind of the same main company. All of them actually is the same. Like one company, they branch to different brand names, and each one provide us with the section details, mostly used locally to form up the steel structure. So one steel give us the section of the steel. Okay, so we got standardized steel sections like universal column, universal beam, hollow sections, open sections. Stramit and Lyset, they gave us information, and they provide the products where we use them as lightweight steel structures, which I will be talking about this more and more. There are other resources we use to build these nodes, and as I said, in each week, like week 2, there is a reading materials. You can look at them, and we use them as required. All right, so talking about loadings and members. The famous or the main loads, industrial buildings will experience dead load, which we all know about. Dead loads comes from the own weight of the steel, the weight of the sheets sitting on the steel frames, and the weight of services that permanently will be there, like mechanical components for the air conditioning units. I'm not talking about the chillers which sits on top of the roof. I'm talking about the ducts, which is not likely to be removed or changed at all. You know, the ducts of the heating and cooling systems, they're going to be there for almost 10, 15 years sitting there. So these are dead loads. Okay, live loads, they are the users, the occupants, the furnitures. If we're talking about the roof, the chillers, the air conditioning units, because they are movable, they can't change. So these are the live loads. Industrial buildings, especially the ones we're talking about, they are very, very, very sensitive to wind load, right? So maybe the library projects or building apartments, they, with the block walls, like the project 10-story apartment building, got a lot of block wall, which sometimes they are even over what you would need for wind load. So, but architecturally you want it there, or maybe the engineer wanted them there for fire rating between the apartments. So sometimes in those apartment buildings, we can easily achieve wind load calculation, and the critical loading would be dead load, live load, right? However, in the buildings we're talking about, industrial buildings like those warehouses, the portal frames, wind load is very sensitive. Usually it can exceed dead load easily, because even the dead load, as we said, they are just a sheet, and the sheet load is very light. It's 40 kilograms per meter square, the weight of a sheet. The steel sheets which sits on the pearl, they're not heavy at all. So wind load, which are covered in points C, D, E, they are all to do with wind load. Okay, so wind load can come across the building, or can come along the building, or can come as an internal pressure, because if that warehouse got its gates open, then the pressure gonna be from inside out. If the gates were closed, then the pressure can come from outside in, and we're gonna see quick examples about this. All right, so this one here shows you a warehouse. It's just the warehouse overall 3D look. Now the portal frames, as I showed you last week, they will be basically sitting, you got one at, I'll try to draw them as much as accurate. This is the first one, if required. Got the first portal frame at the ends, and then you've got them every, say, 6 meters, right? These are the portal frames, they spaced every 6 meters, right? So if we got this wind, I've discussed this point last week. So if we have wind and we're calling them wind in the 0 degrees, who's gonna resist those winds? We call them crosswinds, CW, crosswinds. Which structural element which will resist them? Answers?
Bracing?
No.
Frames.
The portal frames, the red portal frames, because they're gonna be with rigid connections. That's what we're gonna talk about this week and next week. These portal frames, they are called portal because they support themselves, especially in this direction, or particularly in this direction. Yeah, the portal frame is, hopefully I've got a picture soon. Here we go. These are the portal, maybe I have, yeah, better one. This is a better one, a better picture. The portal frame sits like this, okay? And they are intentionally done like this in order to portal itself. The word portal means you're bracing yourself. As I said, if you're standing in a tram or a train and you want to brace yourself, you're gonna kind of open yourself and stiffen up yourself. So when the wind, when the forces or reactions come laterally on you, you can stand against them. Talking about wind loads and portal frames, they're gonna have rigid connections, fully welded, or you're gonna go through all those detailings in terms of construction. Same thing here, same thing there. The moment this will allow the frame to resist flexure, and you can't actually push it. Unlike the situation if you just had pin. What I mean with pin, it's another frame where you've got a beam like this. Let me just draw the beam. You've got just a beam like that, and just put it on two sticks with a very simple, cheap pin connections, which can be just two bolts connecting each other. But this is gonna fail down if you pushed it laterally this way or that way. It's just gonna fall down. And in this case, yes, we need some bracing to put there. But in this buildings we're talking about, we cannot put bracing here. You're just gonna have no access. So we have to use portal frames in the crossways direction. So let me go back to my earlier slide. Yeah, let me go back here. The portal frames, they are in this direction, right? So what I was asking you, if the wind is mainly blowing in the 0 direction, which we're calling it crosswind direction, yeah, 0 degrees, which element gonna resist it? Portal frames. They can withstand lateral loads. Same story. Let me clean up this. Same story for which direction are also. I think they didn't say it to you. If the wind was blowing in the 180 degrees, so this is 0. That means 180 is here. Same story. The portal frames will resist it as well, but it's coming from the opposite direction. Now, let's go to the longitudinal wind. Which element can resist it? Can the red portal frames resist the 90-degree winds?
No.
Why?
Braces are here to do that job.
Correct, because simply the portal frame is going to be tipped over. Someone will say, can we actually come here and put members and do a lot of welding and all those? It's going to be too expensive. Nobody does this. So it's not a typical exercise. Nobody does that. Yes, it's possible, but usually we're going to have we will tell you about this, some eave beams. We call them eave beams. They act as, and they are cheaply connected with the portal frame. So they are with bolts, cheap, not a lot of welding. So, and then we're going to introduce some X bracing. So then X bracing, it's going to work with the eave beams, with the eave H beams, and those columns, they're going to, and the ground, they're going to use the trusses principles you studied at university. There is a truss system. So you can see this triangle. Simply, it's a truss system that will then, in case there is a wind blowing this way, when there is a wind blowing this way, you're going to have the portal frames or the structure stabilized. So you're going to have bracing here, and same thing, bracing on the other side. Yes, we are able to have, even if we have a window, it's fine because it's going to miss the bracing element. So it should be fine. And we have a wall here. We can hide the wall. a quick picture that will help me to explain this to you, it's here. You see, this is what's happening. This is exactly what I'm talking about. These are the portal frames. You're really not understanding, please stop me. All right, don't feel it's, yeah, you see, this is the portal frame and the bracing is here. So that's really what we're talking about. That was the wall. Someone will say externally here we have walls. Yes, but the engineer seems here to decide on still using portal frames. I can see this rigid connection. In some projects like the one you're going to work on, the front ends, they are not portal frames. You're going to see that in your project, your assignment. So in the front side and the back side, you can decide not to have a portal frame. You may decide to simply have an X bracing. Why? Because you got a wall to put the bracing in, right? You can have a simple beam to column connection and get it all done. Is there any question about this slide and what we mean? So one of the points you need to understand with industrial building, like warehouses, they are sensitive to wind load. You need to understand what we mean with crosswinds, what we mean with longitudinal winds, and how they are resisted. Okay, which structural element will resist them? Is there any question about these kind of features or properties?
Sir, if the internal pressure is acting in the upward direction, how can we resist the force?
Can you please say this louder, please, a bit?
If the internal force is acting on the upward direction on the roof, how can we resist the force?
If the internal pressures, you talk about internal pressures, so you talk about internal pressures?
Yeah, yes.
Okay, so the question here, yes, that's a nice question. If there is typically gates here, like doors, and when the doors are open, which is usual in industrial and it's windy, then the wind gonna go inside and then the wind gonna start pushing outward. So let me jump to that elevation, which will help me to explain it. If I go here, what's gonna happen here? The pressures will be pushing this way, right? Internal pressures will be, if they overcome or they are more than the dead load, which is usually the case, then we're gonna have pressures pushing upwards. Now, if the pressures, the lateral pressure, same story. The lateral pressures from the internal pressures, they're gonna be resisted by the portal frames. If we worried about these directions, left and right, portal frames will do the job. Same thing, if you worried about the pressures pushing up, portal frame, they do the job as well. And one of the checks, we have to make sure the footing gonna be heavy enough. And that's what the engineers do, and that's what you need to build. That's why I'm gonna talk to you maybe this week or next week about special bolting we have to have here to make sure when the portal frame is getting lifted up, it's adequately connected to the concrete footing, so the weight will counter it back down. Does this answer your question, or you had something else?
Yes, sir. No.
Okay, good. So any other questions about the wind load briefing? Right, now what I'm showing you here, I can tell you, it's kind of the structural engineer's work. It's not really the construction engineer, but he just, again, as I said, construction engineers needs to know what's in the background. So that's really what they do. They calculate the values. You see the dead load. It's positive. That means it's going down, and it's only 12.8. See how small? I'm just letting you sense the numbers, because I just told you before, industrial building are sensitive to wind, and this is at exact numbers from an example done for same projects. See what's happening here with the dead load. It's only 12 kilonewtons, right? Which is about 1,300 kilograms. Okay, pushing downward from the dead weight of the structure, because it's only light sheets. See what the wind is doing. It's negatively pushing up. Yeah, and that's why engineers gonna make sure the concrete or the pile at the column gonna actually take things down. And that's where the builder need to understand that concept and intent and make sure things are built correctly, not using normal bolts. Same thing. So that was the crosswinds, that was the longitudinal winds, and internal pressures, they are a bit lighter because you have the dead load pushing things down. Okay. Horizontal loads, same thing. You can see the wind is always winning and really critical, really critical. Okay. So what the engineers do really, they don't only consider one wind, there is a combination of load. They combine the loads. All right. I can tell you, you won't be asked to do such calculations. This is not part of what this subject is about to you. I'm here trying to let you know the thinking that engineers go through to really do the drawings to you. And that's what you need to consider. So this side is talking about the loadings and how it will end up impacting the footing, which will determine the size of the footing and how we connecting the columns to them, which we talk about this today or next week as well. So maybe tomorrow I will show you how really we connect physically the column to a footing. It's not just a bolt screwing. No, there is a special cage, and all that cage is made to take out those high forces. It's about 80 to 100, so 8220. It's a lot of kilograms, many kilograms. Okay. That's one point from the slide. Deflections, as I said to you, yes, the engineers will be calculating. The engineers, by the way, he may give you, as we're going to see in your assignment one project, he or she, the engineers, will give you an idea what you should estimate in having after you actually build it. So you need to make sure this is what happened. Don't say it's not my job, because as I said, there may be the wind may be blowing a lot and over deflecting. They may be, you are the first contact person to, I don't want to say to blame, but to let you investigate the problem. And maybe the way you connect things is wrong. You made it with a pin, so you over sagged it. Maybe the beam you ordered, they come pre-sagged in the wrong way. So there's a lot of things can happen. So you need to know deflections is something the clients we worry about. They need to be within acceptable limits. For example, industrial buildings, the maximum deflection that we are allowed to have when the roof is pitched at above more than 3 degrees is span over 360. So if your warehouse was about like this D was about 20 meters, then you divide 20,000 millimeters over 360. It will give you how many millimeters you are allowed to, ideally by, acceptable limits by standards. So at least you're going to start warning. You're going to start, if you see you have about 100 mil deflection, that's a problem. 100 mil, it's a lot of deflection. Yeah, it's not acceptable. 40 mil like this acceptable, and usually there are limits available by many documents for the builders to check with. That's from dead load. Live load, if you maybe start placing furnitures or talking about warehouse, if you start putting some chillers, like you have some air conditioning unit placed on one side of your warehouse, right? You are start putting in the back here some chillers, some air conditioning units here and there, and then you have to do that check in making sure the beams have not deflected a lot and they still within acceptable limits. Like here, that's where you use such documents. You are the builder. You are the one who is really making sure everything is in the right order. If it's not working, you can go back to the engineer and tell him why this is deflected. It was written on the architectural drawings that there are units and they're supposed to be strong enough to take such deflection, because it won't be acceptable. The job can be rejected. So that's where, by the point of the information here on the slide, there are limitations for deflections to check with. Okay. All right, now we're coming to loads on members. Still, this will be kind of what I start briefing you. First main element we have here, it is Mr. Portal columns. Okay, so here we're talking about the members that will form a portal frame. As I said, this is a portal frame. This element here is the portal frame. The first element I'm talking about in that slide, it is a portal column. Okay, the word or the two words portal frame is different than portal column. Portal column is different than column. Column, it's like any piece of vertical element carrying something, regardless how it's connected to the beam above. When we say portal column, it means that the column, it's fully connected with the beam. Fully connected means it can take all actions on it. Actions, if you remember when you studied at university, you've got bending, you've got shear, you've got compression. When we say portal column, it means that that column can take all those actions, because that's what the engineer thought about, and that's what the construction engineer need to think about when he built it. Okay, so portal columns allowed to take all type of action, compression stresses, flexure, and about all directions. That's the point of having a portal columns. Okay, that's the main thing you need to understand. Their lengths are again, their effective lengths. They really, the portal columns, when they are designed, so this is the portal column here, and later on we're going to talk about how it's welded, fully welded and connected. I should not say welded, because there is also bolts, and bolts are designed to take all those three actions, whether compression, shear, or flexure. Okay, here, these are the portal columns, and they depend on how they are braced. Who is bracing them here? The girts. The girts are actually helping to design, and that's the point of the second statement. So their effective lengths, yes, it is the spacing between the girts, because the girts are helping them to stabilize. Someone may ask me, what about these elements? They are the fly bracings. Now, this is a bit critical thing, and we're going to talk more and more about it maybe during the workshop. What I want you to understand here is we are actually laterally bracing the columns from both sides, the far end and the close end. The far end is that flange in the back. The flange, you know what flange means, guys? The flange, if I quickly drew a section, this is a section of a column. Yeah, that's the cross section for a column when I cut it here. This is called a flange, in case you don't know the terminology. This is the top flange, or one side of the flange. This is another flange. Yes, and this is the one in the middle. This one is called what? A web, W-E-B, a web. Right, a web. And the top one and the bottom one, it's called a flange. So what I'm trying to point out here, when engineers, and same as when the construction engineers build this, they need to understand is those skirts are not just connected to vertically carry themselves. No, the girts are actually helping the column, because the girts gonna actually tie it. Now, the back flange, it's actually restrained over these distances, which is say about a meter. Okay. However, the front flanges here, they are braced by Mr. Fly bracing, these guys. And these things, what you need to understand, they are engineered. What does it mean engineered? They are doing a job which I will talk to you about during the workshop, because we will start asking you details there. Okay, so they are structural elements, needs to be constructed if not constructed, it means that the portal frame is still weak. And someone will tell me, maybe I built those ones without the wall. How come I'm gonna use them? Then you have to brace it. You have to physically put some props and brace it, because the portal frame will not work, because its strength is coming from the help of the girts. It's kind of holding it, and we will talk about this over the workshops. So that was the second point. Their effective lengths are determined by how the girts and the fly bracing are connected to it. Okay. There are stresses you need to know about. Maybe you know that from school. You know, these statements here, they just summarize what I talked to you. The inside flange compression, outside flange and compression. What I mean inside and outside is this is the outside flange and this one here is the inside. If the wind is blowing this way, which side is compressed? We'll say this is orange and this is what? Green. If the wind is blowing this way, which side gonna be compressed, the orange or the green? Imagine, use imagination. If the wind is blowing this way, from out to in, which flange gonna be compressed?
Orange.
Orange.
The one who said the green is correct. The one who said the green is correct. The green. Why? Because you're gonna be flexing the beam. Let me use a blue color there. You're gonna be flexing the beam like this. Yeah, when you flex the beam like this, this is the compressed side, and this is the tension side. Okay, so this is your beam. When you're gonna be putting a pressure this way, outside in, you're gonna be flexing it, curving it like that. Usually this side gonna be under compression, and this side is under tension. Now, one thing I want you to understand, the beams are very sensitive to compression because they're gonna buckle. If you over compress a flange, it's gonna buckle. And that's why what we're saying, we're gonna, to prevent that buckling, we're gonna have the girts helping that beam or flange from getting buckled. Okay. So if the wind was coming from inside out, the story gonna change. The orange will be under compression and the green, the outside gonna be tension and the inside gonna be under compression. Okay, so the message you really need to understand from here, and we're gonna talk about it during workshop slowly, is the girts, which are now connected to the columns, portal columns, and the fly bracing, which are these elements, they are there to restrain, confine the flanges, whether internal or external, because those flanges can be under compression, depends on the wind. If the wind is from outside in, the compression gonna be on the outer side flange here. If the wind is from inside out due to internal pressure, this flange will be under compression. Then who will help it to prevent that buckling? Because usually if you compress that flange a lot, because you're flexing the beam like this, yeah, you're gonna create a lot of compression here. To stop that from happening, you're gonna use actually those fly bracing to make it more strong. All right. These questions, we're gonna practice them more and more during your workshop questions. All right. So you're more than welcome, guys, to always, if you don't want more clarification, send me email or give me a call. We meet separate times and discuss, let you know more about this. These are kind of questions you need to know. So that was one of the members, the famous guys in the portal frame. Portal frame, the main guy here. This is called a portal frame. I'm just here, I know some students are new to these terminologies. This whole guy is called a portal frame. This element, which we just finished, it's called what? Portal column. The other element I will talk to you about before we end the lecture, it's this one, the rafters. This is called a rafter. This is called another rafter, and that's the stories behind them. The good thing about the rafters and the information I want to teach you about rafters, it's got the same story. This is the rafter we're talking about. Same thing, it's gonna suffer from compression and tension. Now, if I will put dead loads, maybe we have a nice day without wind and we only have dead loads. which side is compressed? You tell me, guys. Try to throw it to me quickly. If we got just maybe even if wind load and dead load are coming from up down the page, up down the page, which side gonna be compressed? Is it the red side or the blue side? I will zoom in. Yes, which side gonna be under compression when the load is coming up down the page?
Blue side.
Blue side.
Excellent. Blue. Yes, blue side gonna be compressed. Why? You have to use imagination with this. This is how the beam or the portal or the rafter gonna behave. When you're gonna curve something, like hold on a book, you're gonna camber it like curve it like this. You're actually compressing the top surface. You're compressing this side, yeah? And you are tensioning the lower side. You're tensioning this side. So that's simply the concept. I just want you to imagine it. I don't want you to do the calculations. You did it at your engineering course before. Now, if the internal pressure is going down, up this way was winning, which side gonna be compressed? The lower side or the upper, the lower flange or the upper flange?
The lower flange.
Correct. The lower flange. Correct. The lower flange will be compressed. So let's come back to this friend here. Yes, to this, I think what I'm taking you through are the main things I want you to understand, because it will help you to correctly answer some critical questions. So this is our beam. You know, same story with column. The beams are horizontal or a bit sloping. The columns are vertical, but same story. These are the bottom flange, top flange, and this is the web. You can see, as I said, engineers, when they do the calculations, they find a lot, sometimes when the wind is going down, up, there is a lot of compression on this guy, on this side, on this flange. We don't need, if he or she don't use these elements, what's going to happen? You will be inefficient. You have to go to a bigger beam. But why are you doing this? Just use some cheap fly bracing materials every 2 meters or every 3 meters on the critical points, and happy days. That's it. You can still use the same small size and everything gonna work because you stopped the buckling. If we did not put those and we kept the size small, this flange will buckle. What buckle means? The beam gonna be twisted. It will actually go like that. Yeah, it will be twisting like this. It will just twist. And this is a damage. This is a damage. Right? So that's why these fly bracing needs to be. So they help the bottom flange to work. Who's helping the top flange? It's the purlin. The purlin, because these guys are the purlin. See this little guy here flying up? It is the purlin. And this is the rafter. Okay? So these two definitions, guys, I want to take you through. They are, I wanted to finish them today. Because I just want you to start understanding a few first terminologies. Number one, the portal frame columns. Portal columns, read it. The rafters, read it. The purlins and girts. I know the other slides, they're really easy to go through. I will cover them tomorrow at the start of our workshop. So same thing, we're gonna have some time to end up, but they're gonna be helping us also with the questions, because I know some students at the start, they just building their knowledge and learning about terminologies. So let's stop here at the frame design. And tomorrow I will continue from this point on. But please make sure if from now until Wednesday, these slides did not make sense to you, it will be very slow for you to build what's coming next. And I do see, unfortunately, some students, even when their first assignment submission, they don't know what I just said. They still don't understand what I mean bracing and internal pressure and buckling and which side gonna be under compression, tension. Some of you maybe, especially people who may who did not really attend and listen to what I'm talking about. So if you like, just make sure you are on top of the the slides up to here. If you want to stop here, that's fine. I will continue the next 20 or so sheets. They should be simpler than the concept we covered. Then Wednesday, I will start solving 3-4 questions. I will introduce assignment 1. I expect all students are listening or coming to wherever we have to be, and we start answering the questions so you can progress on assignment 1. Okay? And that's it for today. Any questions? I'll stop recording. And this record